After we know about the concept of the local and global PSO, and then I'm going to talk a little bit more about different aspects. Yeah, the first one, that is the velocity component that is associated with the update rule VIT plus 1. Okay, so when we talk about the velocity component, actually we can break it down into three components: the period velocity, connective component, as well as the social component. No matter it is for G best or the L best, we have these three components. And so if you are going to look into a little bit details, and then we will find out that different characteristic is associated with different component. Yeah. So for example, when we talk about the social component, that is this component is known by everyone. If you talk about the global best, and then the social component that is related to the global best solution. And then for the social component of the local best, that is associated with the local best component within a neighborhood. Yeah. And the connective component, that is the information collected by the particle itself, that is the personal best position. Yeah. The previous velocity right here, that is the inertia of the of a particle, yeah, from the beginning. And then so in general we can just consider that the previous velocity, that is the inertia making the particle move in the same direction for the coming iteration. So the previous velocity, that is for exploration. So it helps the particle to explore some new area. Yeah. And then for the social and connective component, there is something about the history, the historical information. So it is more about the exploitation. So it search for the some previous long region with some good solution. Yeah. So with the adjustment of the C1, C2, as well as the random number R1, R2, we can adjust the weight of the connective component and social component. And so in a figure, so when you refer to all these three components in a graph, it is a vector, because when we talk about V, Y minus X, Y hat minus X, actually it is a vector. So assume that this is the current position, xt, and then when we compute VIT plus 1, we can break it down into this VI at t iteration. So this is the inertial velocity, and then the second component, connective velocity, it always points to the personal best position, and the social velocity, it always points to the global best position or the local best position. Yeah. So when these three elements, they are added together according to this update rule, and then we will have a new position right here. It depends on which one takes the heaviest weight. For example, this one, the social velocity takes a heavy weight, so the xt plus 1 points toward the y hat, the local best the global best position. So after the particle move from xt to xt plus 1, that is in this point, after we update the local best as well as the personal best position, and then so we are going to generate the random number R again, and then compute all these three components. And now this time we still have the three components: inertia, velocity, and the social velocity, as well as the connective velocity. Now this component has a heavy rate because of whatever reason. Now anyway, after we compute the new velocity, so this time it points in the middle. Yeah, it points in the middle of the local and global best solution. So with the parameters C1, C2, as well as the random number, we can adjust the weight so that to determine whether we are going to put heavy weight on the exploitation or exploration. Yeah. Okay, so this is the velocity components, and then next topic I'm going to talk about, that is the particle initialization. That is, how do we generate the initialized swarm? So In the beginning, I mentioned that we have a number of particles x1, x2, up to xn s, and then this is the population. So in some cases, we would like to generate the particles within bound. So this bound that is for the j component that is bounded by x min j or x max j. So what I mean, that is something like this. We have particle. This particle can be any one of them right here, depending on the value of I. Yeah. Say if we would like to have this x1, xi1 bounded by -5, 10, and then we can use this equation. Yeah. Initially, we are going to choose x min j. J at the moment, that is 1. Yeah. Because we talk about the first position. This is -5, and then rj, that is r1, that is a random number in the range of 0 to 1. X max, that is 10 according to this example. And then this one, that is -5. So what we are going to do is just to generate a random number right here. So this, using this expression, we can make sure that a number, a value for xi1 is generated in between -5 to 10. Yeah. So go through all the components and go through all the population, and then we can generate the initial population or initial swarm. For velocity, the simple way, that is, we just set it to be 0. This 0 in boldface, it doesn't mean that it is just one single value. Yeah, so this is a vector. It means that all the elements, they are 0. Yeah, so v1, v2, we have 0. This one, whether this is 0 or not, it is up to us. If we would like to use a small value or a random number, it is also fine. Yeah. For the personal best position, because this is the initial value we don't have any historical data, so the personal best position, that is the particle itself in the beginning. And stopping criteria, we have a lot of options. The first one is very straightforward, that is, we are going to set a maximum number of iterations. That means we are going to run the algorithm for say 1000 times and then stop. Another one, that is acceptable solution, has been found. Say if we would like to have the cost that is lower than 1000, and then if the condition has been met, stop. Or we are going to check low improvement has been observed over a period of iteration. For example, we are going to check the global best, maybe t minus 5 up to the current t, y hat, yeah, up to the current iteration. If the improvement is very small for the past 5 iteration, the global best solution does not change much, and then we stop. Yeah, so this criterion can be used for the global best or the local best PSO as well, because for the local best PSO we can still find the global best. Yeah, and the swarm radius is close to 0. Yeah, this involves the term swarm radius. I'm going to talk about this later on in the next slide. And then, or we can compute the objective function slope. This is the slope, the cost of the global best solution minus the previous global best solution divided by fy hat, and then so we are going to monitor this value for some consecutive iteration. We define how many iterations we are going to monitor. If it is less than a chosen epsilon value larger than 0, and then we are going to stop. Yeah. And in the next slide, I'm going to show you the swarm radius method. Actually, we have 2 methods. The first one, that is the maximum swarm radius. The next one, that is the particle clustering method. And now this algorithm, when we talk about the maximum swarm radius, the algorithm terminates if the maximum radius that is less than a chosen positive value. Yeah. So if it is less than or equal to epsilon, we stop. Otherwise, we are going to carry on. Okay, so this is the Rmax, the definition of the Rmax. And so we will calculate the distance between the particle and the global best position. Yeah, again, for the global best or local best, we can still find the global best position. Yeah, okay. This one, I'm going to illustrate that using the next slide. How do we apply this condition? This is the maximum swarm radius. So according to what we have right here, we need to, at the iteration t, we need to find the global best position. And then I assume that this is the global best position right here. We have a number of particles. Assume that the swarm size, that is 7. So we have x1, x2 up to x7. So now according to what we are going to do right here, that is to find the distance between each particle with the global best position. So we are going to do this. x1 minus y hat, and then L2 long, that is the distance right here. So if we are going to talk about x1, that is 2 particles, x11, x12, and then y hat, we will have y1 and y2, 2 elements. This L2 long, it means we are going to do x11 minus y1 square plus x12 minus y2 square. Take the square root, and then this is the distance right here. So we compute the distance between x2 and y hat, and then continue to for the rest of the particles. Now we are going to find the one which gives you the maximum distance. For example, this is x5, and we come up with, when we exercise this expression, we just pick the one. Yeah, we just pick the one. This means that the maximum distance for this group of particle from 1 to 7, pick the one, give you the maximum radius, that is x5. So this is the Rmax, and then check whether Rmax, that is less than the predefined value epsilon. If it does, we stop. Otherwise, we are going to carry on. So the physical meaning is that we are going to measure the how close the particle to the global best solution. If they are very close to the global best solution, and then we stop. And now the second method, that is the particle clustering algorithm. We are going to use the clustering algorithm to determine how close to solution they are. I mean how close the current swarm they are. Yeah. So what we're going to do is that this is the pseudocode. We are going to initialize the cluster. So that means C represent the cluster. That means in the beginning we are going to insert the global best into this cluster so that this cluster has only one member, and then we are going to repeat this process for 5 times. Why 5 times? But not wait for the algorithm converge, because of we would like to save the computational power. Because if we are going to wait until the algorithm stop, don't forget that we are going to run this algorithm for each iteration. If the population size that is large, and then it will be very computational expensive. So what we are going to do is just to get a sense how close these particles they are. So we do not need to wait for the convergence of the algorithm. But anyway, this is just 5 times. If you do not like to have 5 times, and then so you can increase it to 10. Yeah, it is still possible. So when we get to this line, and then so this line, that is to calculate the centroid of cluster. That means we are going to compute x bar t, that is the center of the cluster, in defined right here. So I, that is this I, the particle I, from I to absolute value of c. Yeah, so I have to emphasize that this straight line C, it doesn't mean the absolute value. It represents the number of elements in cluster C. Say right here, we only have one member, so C, straight line C, that is 1. So that means we only need to work on the elements within this set. Yeah, so we do not consider all X in the population. We only consider the X in this set. In the next slide, I'm going to show you an example. So anyway, we compute X bar. Using this X bar, we are going to calculate the distance for all particles. So the distance between xi minus x bar, that I that is going through from 1, 2 up to the last particle. Yeah, if the distance is small enough, that is smaller than or equal to a predefined value of epsilon, and then so we are going to insert this particle into the cluster C. Yeah, so the size of the C is increasing. Yeah, so we repeat this process and go back to the top until we perform this iteration 5 times, and then so we will have the value of C based on the number of member in this cluster. So C divided by NS, that is the number of elements or number of particles in the population that is close enough to the central to the center X bar, and then divided by NS, that is the percentage of the particles within epsilon. And then if it is larger than delta, this is a number, a value defined by the user. Yeah, so if it is more than a number, more than delta, and then we are going to stop. Yeah, that means the algorithm, the PSO algorithm, stops, and otherwise we are going to continue. And take a look at this example using the swarm radius particle clustering algorithm. So initially, that is, we are now at this point. So that's why when we compute the y hat, that is the global best solution, initially we only have one element in C. So we come up with this line, and then when we calculate this equation, yeah, when we calculate this mathematical expression, C, that is just one component. So that's why X bar, that is y hat. Now we go to this block, and then we compute the distance between xi to x bar. So that is equivalent to find out the distance between x1 to x bar, x2 to x bar at the moment, that is y hat. Yeah, and after that we are going to determine which elements or which particle should go to the cluster C. Now that means according to the chosen value of epsilon, that means we draw a circle with the center x bar. Now this statement just mentioned that if xi minus x bar less than epsilon, that means this particle is within the circle. We are going to insert that into the cluster. So we are going to check one by one. x1 outside the circle, we do not need to consider that. x2 within the circle, so we need to insert that into the cluster. And then x3 no, x4 yes, and so and so. So we just find out that next we have, after we perform this block, we have the updated C, that is y hat x2, x4, because x2, x4, they are within this circle. And then go back to this top, yeah, because we have to repeat this for 5 times. Yeah, so we go to this line, that is, we are going to compute the new x hat, yeah, sorry, the x bar, that is y hat plus x2 plus x4 divided by 3, because we only have 3 elements, 3 members right here. So this x bar would be somewhere in the space, that is the new centroid for the particle clustering algorithm. Now, after 5 times, we are going to check this condition. If this condition is met, we stop. Otherwise, we continue the PSO algorithm. Okay. So now we look at the social network structure. That is just one slide. I just want to emphasize that we have the global best and local best PSO. When we talk about the global best PSO, the label, that is the whole swarm. So when you look at this network, that is fully connected network, that means the information will be passed on to every one of the particles. That is the global best solution. So when we talk about the West network structure, for example, the ring, the pyramid, so and so, they are not fully connected network, and then so that means those particles, they form neighborhood, and then all this network, all the West network, we will use that in the local best PSO.